Okay, welcome to the first video I've shot for my YouTube page in a few years. We're in a new building. You won't see the old crappy office. This is for Chem 223 in the spring semester of 2020. It's spring break. It's Monday of spring break. Hopefully all the students are out on a beach somewhere and are going to watch this and work some problems later tonight. If you are somewhere else in the world, this is second semester organic chemistry at Wake Forest. Okay, so the problem is, here's how it's going to work. I'm going to present the problem. I'm going to tell you to push pause, and you go away and work it. Okay, so come back. The problem is this. We've got this green aldehyde here, and we're going to treat it with ethanolic HCl. So we're going to take the green aldehyde, and I just mean the ink is green. We're going to take that aldehyde. We're going to dissolve it in ethanol. We're going to add a little bit of HCl. We're going to stir it. Maybe we'll heat it. Let me put one other thing here. So I'm going to put some magnesium sulfate in there, some anhydrous magnesium sulfate. Okay, we're going to get a product out of this, product A. I want you to pause now and come back and draw compound A. Okay, hit pause, figure out what A is, hit play, and I'll show you what A is. Okay, so hopefully you actually did that. Hopefully you're not just sitting there if you are just sitting there watching the video, watching me work these problems, that won't do it. You got to work the problems yourself. So compound A, if you don't already have it, stop again, stop, pause, and actually go do this. Okay, so we've got catalytic acid, we've got a weak nucleophile in ethanol, we've got an aldehyde, so this is going to make an acetal. The magnesium sulfate is going to serve the purpose of the drying agent, so that's going to soak up any water that's produced. You can also use a Dean Stark trap, you can reflux this, you can use molecular sieves. The magnesium sulfate is just kind of a hint that you need to solve it. Okay, so our acetal, everything else in this molecule is going to stay the same. We're not going to affect the chiral center, because it's not an enolizable position. We're just going to add 2 ethoxys to that carbonyl oxygen. So make sure you get that stereocenter in there. One more carbon, there's another carbon, and there's our aldehyde carbon. So O-ethyl, O-ethyl. All right, there's the acetal that we make. So again, there's no redox in this reaction. This carbon here, the aldehyde carbonyl carbon, has 2 bonds to oxygen. The acetal CH has 2 bonds to oxygen. Okay, so now the next part of the problem is I've got a whole bunch of reactions written in black ink here. Figure out what happens to those. So take the acetal, treat with lithium aluminum hydride and water. What happens? Same thing with our starting aldehyde, lithium aluminum hydride and water. What happens? Then Grignard to both of them. And finally, what happens if you treat the acetal with H3O+, that is aqueous acid. So aqueous HCl, aqueous sulfuric acid, something like that. So hit pause, go away and work these problems, and then come back and I'll show you the solutions. Seriously, can't tell if I'm on camera or not. Seriously, hit pause, go work the problems. Okay. Hopefully you're back. So first of all, let's do the lithium aluminum hydride reactions. LAH here. Lithium aluminum hydride is going to reduce that carbonyl. And aldehyde's really pretty easy to reduce. And so lithium aluminum hydride does that well. Sodium borohydride would give you the same product here. So that, again, we're not going to touch this chiral center. So leave everything in the molecule the same. We're going to work this LAH reduction up with some water carefully. So we're going to just end up with an alcohol here. The hydride adds there. You essentially have a hydride minus adding into that carbonyl carbon. Pop the electrons up on the oxygen. That oxygen actually bonds with the aluminum. And then when you hydrolyze it, you protonate the OH. Okay, there's your product. What about over here with the acetal? When we hit the acetal with lithium aluminum hydride, do we get the same product? And the answer is no. One of the important points of why you would make an acetal is it protects the carbonyl from reaction with strong nucleophiles. Okay, so this aldehyde is susceptible to hydride nucleophile. The acetal's not. So nothing happens here. No reaction on that. The acetal is impervious to nucleophilic reagents. Come back over here to the Grignard, methyl Grignard, followed by water, same thing. That methyl Grignard is going to add into the carbonyl. We're not going to touch the chiral center. Water is going to come along and protonate that methyl, so we add that methyl there. Okay? So strong nucleophile, the aldehyde is really susceptible to both of those. For the acetal, methyl Grignard doesn't do anything. Okay, methyl Grignard isn't going to do anything, water is not going to do anything at the end, so no reaction there. So you might get the idea that acetals aren't very reactive. And it's true that acetals aren't as reactive to nucleophiles and bases as the carbonyl. So we would call this acetal a protected aldehyde. Okay, so if this is a pretty simple molecule, there's not really a lot of other functional groups to do it in chemistry with. But if there was chemistry that we wanted to do basic or nucleophilic chemistry on, we would need to protect this aldehyde in order to keep it from reacting with whatever that base or nucleophile was. The other thing, part of a protecting group, so an acetal is a way to protect the aldehyde, but if it's really protected instead of just destroyed, you've got to be able to get it back. And so that's going to be, the way we get the aldehyde back is we treat it with aqueous acid. So this is just going to give us our aldehyde back, right? I didn't draw it there, but there's an H on that carbon, remember? Back to fundamentals, carbon gets 4 bonds. Keep track of where your carbons are. The other thing to keep in mind as you draw products like this is count your carbons. 1, 2, 3, 4, 5, 6, 7. Should be 7 carbons in all of these. 1, 2, 3, 4, 5, 6, 7. Guess there should be 8 when we add a methyl. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. It's really easy to screw that up as you're, especially on an exam or a quiz, as you're sort of blowing through it fast. It'd be real easy to take a carbon out here, stick another carbon in. As long as you draw your lines kind of zigzag, make sure everything points the same way. They don't have to, of course, but it's a good idea. Okay, so here's another thing you can do. Go away and try to name this compound. So hit pause and try to name it. And then draw it into ChemDraw and see what ChemDraw tells you. That's the easiest way to do it. Do that for all of these compounds. All right?